let's now work through this example that's in the notes. This is just a pretty straightforward question, just to help you to get used to the process. So it says, prove by mathematical induction that for all integers n greater than or equal to 1, that 1 cubed, 2 cubed, up to n is equal to 1/4 n squared, n plus 1 squared. So let's have a look at the solution. I've copied this, just cut and paste this straight from the notes. Step 1, show the statement is true for n is equal to 1. You know, with any show question, we take the left-hand side, work with the left-hand side. If we can turn it into the right-hand side, great. Otherwise, we then take the right-hand side and work with it and hopefully show that they're both equal to the same thing, which is what will happen in this case. So, showing that the left-hand side is true for n is equal to 1, well, we only want to go to 1, so it's just 1 cubed, and 1 cubed is 1. So, I'm stuck. I'm stuck with that. I can't go any further. So, like I just said, if that happens, then we take the right-hand side, and it is 1/4 n squared, n plus 1 all squared, and we're showing that it is true for n is equal to 1. So it's 1/4 times 1 times 1 plus 1 is 2, and 2 squared is 4. These cancel and you get 1. We've got the left-hand side equaling 1, the right-hand side equaling 1. If they're both equal to 1, therefore the left-hand side equals the right-hand side. Therefore, statement true for n is equal to 1. Now we do that because n is a nice easy number to work with, and just be aware that there are times where you'll see the condition on n might be n has to be greater than 4, or n has to be greater than 2. So we wouldn't prove it true for 1 if it said n had to start at 2 or 4. So, like I said, you'll see all these variations and hopefully you'll be able to make the appropriate change as they come along. Okay, step 2 was assume true for then n is equal to k. That is, we write this out in terms of k. So we'd have 1 cubed plus 2 cubed plus 3 cubed, dot, 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 up to and including k cubed would be 1/4 k squared k plus 1 all squared. All good so far? Step 3, or paragraph 3. Show true, now this is the recursive bit, for n equals the very next integer after k. That is, what would that look like? What is this statement that I'm trying to show or prove? Actually, I might change that to prove. True for n equals k plus 1. So, what I'm trying to prove is this. Now, I'm going to put that term in, k plus 1 cubed. So I've just gone to the very next term, and that should then be equal to 1/4 k plus 1 squared. Remember, and we're replacing this k with a k plus 1, and that becomes k plus 2 squared. Now, just like for all prove questions, we take the left-hand side, What is the left-hand side? It's what I've just written out. The reason that I write it out in this format is so that I can clearly see now a connection between this and step 2. So part of this series is a statement from step 2. So it says that by logic, in my left-hand side, I could actually replace this section with this, because we've said back here they are true. So this section becomes 1/4 k squared, k plus 1 all squared, and then I've got k plus 1 cubed. Now, that does not look like this. Remember what we're trying to get my left-hand side equal to this right-hand side. What are some obvious differences between this that I have at the moment and where I'm going, what I want? Well, clearly in this expression here, all the terms are being multiplied. All the terms are multiplied. Here, I've got 2 terms being added. What is the technique that we know will allow me to take an expression with an addition sign and turn it into an expression with multiplication signs? Hopefully this has rung loud and clear in your mind, and we know that we're going to factorise this. Can we factorise it? Are there common terms? And yes, of course there are. The common term is I could take out a k plus 1 all squared. It's here in the first term, and it's here plus more in the second term. When I take it out of the first term, I'm left with 1/4 k squared. And when I take it out of here, I'm left with k plus 1. This is looking a little more like what I'd like, and I've got 1/4 k squared plus k plus 1. But it's still not right. It's still not what I want. I'm really happy with the k plus 1 all squared, but I'm not seeing k plus 2 squared, and I'm not seeing 1/4. Now what you're going to see in this next step, you will probably be thinking, oh, I would never have known to do that, and how am I ever going to know to do that in the future? But let me just say, once you've seen it, it's like so many of those techniques that you've come across already this year where you'd not seen it before, but now you have, they just seem to be things that stick, and you go, okay, that's pretty simple, I know I'll be able to remember that. So what I'm going to do is actually, it's in this bracket where I want a difference. I'm going to, and it's probably not so unusual, I'm going to I'm going to write these 2 terms with 4 in the denominator. If I had this k term with a 4 in the denominator, and I had this 1 term with a 4 in the denominator, at least then I'd be able to take the 1/4 out. And that would get me closer to this, and I already have that, and then I would just be hoping this would turn up. So some of you will be able to see that, yes, that is going to be possible. Before I go on to that line, how do I write k, 1k, with a 4 in the denominator? Well, I just want the coefficient to be 1, so it's 4 on 4. Likewise, here with 1, I want 4 on 4, and 4 times 1, of course, is 4. 4 over 1, 4 is 1. What does that enable me to do? exactly what I just said. It enables me to take out the 1/4. And what am I left with? I'm left with k squared plus 4k plus 4. And what do I recognise that as? And even if I didn't recognise it, I would be checking, is it actually this? Square the first, twice the product of the two, square the last. Yes, it is. So this becomes 1/4 k plus 1 all squared, and this is the expansion for k plus 2 all squared. How nice was that? So I've been able to take the left-hand side and turn it into the right-hand side and conclude, therefore, true for n is equal to k plus 1. I proved true this statement back here. We're really done. Step 4 is just to tidy it up and then say, therefore, the statement is true for all n, was it greater than or equal to 1? And that's mathematical induction.